It'd be interesting to see what I've got when I get into these files. Okay. That's an F. If y equals f of x equals 2 to the x. And we're very familiar with that function and how to construct it. Or v of x equals a f of x minus h plus k, which is a times 2 to the x minus h plus k. You vertically stretch this thing by factor a. If a is negative, you flip it over the axis, and then you move your red dot, h units in the x direction, k units in the y direction. You've got a perfectly good exponential function. I have to assume you know how to do that because we've talked about this several times, but you want to continue to think about it. We're not going to be doing too much with transformations right now, but you want to see that as part of the picture. Now, what we want to look at right now other exponential functions have the form y equals b to the x, where b is greater than 0. Okay. And of course, we can do transformations on these just like we do transformations on these. Now let's see what a y equals b to the x looks like. It was of course, and there's an S in course, okay? For example, b is 1/2. Y equals 1/2 to the x. Okay. Now 1/2 to the x by your laws of exponents is 1 to the x, which is just 1 divided by 2 to the x, which is 2 to the x equals 2 to the negative x. This is closely related to the 2 to the x function. How is it related? Instead of x, you've got negative x. What happens if you replace x by negative x? That's a transformation. So let's just say here you've got your school kid exponential function. You know what the shape is. You can construct an accurate graph, but there's your y equals 2 to the x. Okay. 2 to the negative x is just this thing reflected around the y-axis. We've just replaced x by negative x, So whatever the value is at an x on this side, the value of the other function is the same for the x on this side. If that makes sense. It's a coherent statement. It's a little bit complex, so it might be a little difficult to understand, but go back and review transformations. We haven't talked much about reflections across the y-axis, but they're important. And this is where they become important. Now we've done tables for y equals 3 to the x. Remember, we can go back to tables to construct, we use tables to construct our toolkit functions. Same x value that we use to construct the 2 to the x function. We don't use negative 1/2 or 1/2 because we can't write out the value of 3 to the 1/2 or 3 to the negative 1/2 exactly. And you don't know how to calculate it. You'd have to use a calculator. We don't want to have to use a calculator to construct these graphs. All these graphs can be constructed, any of these graphs can be constructed without reference to a calculator. So we want to use our own brains to construct these. We don't want to pollute things with a calculator. We can do that when it becomes necessary to use a calculator, and often it is, but it isn't here. So anyhow, our values are 1/9, 1/3, 1, 3, and 9. And I'm not going to go through the details of why that is. You know how to evaluate it for the 2 to the x function. And remember, at any point, I can ask you to construct that graph and explain it, okay? In other words, construct it from a table and explain it. So you need to remember that much of your arithmetic and rules for exponents, okay? So we have y equals 3 to the x. Right there is a table. If we do a graph, graph's going to go all the way up to y equals 9. Here's x equals negative 2. Here's x equals 2. And if y is 9 here, then y equals 3 might be about here, and y equals 1 about here. And then, of course, x equals negative 1 here, x equals 1 here. We would also need a line for y equals 1/3 and a line for y equals 1/9. Y equals 1/3 would be 3 times as close to the x-axis as the y equals 1 line, so I can kind of draw that. Pretty close to the x-axis. And to draw a line 3 times this close to the x-axis is kind of impractical. So we're just going to say our points are like here, 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 and here. And our curve looks like this, which looks just a whole lot like the 2 to the x function, doesn't it? And of course, 2 to the x function would be constructed in a green box here with a red dot at the origin. And you'd have different lines down here. And you'd have points like here and a little higher here. Point would be through y equals 1, but then we'd only go up to y equals 2, and finally y equals 4. So our y equals 2 to the x function is down here. Bigger the number, the bigger our base, the higher the graph is going to go. Just from these two graphs, it's reasonable to think that for different values of b, first place, all our graphs are going to go through the point 0, 1. And if we graph these things from x equals -2 to x equals 2, we get things like 2 to the x function. But then we can get a function like this. We could get a function that's somewhat shallower, if that term makes any sense. And then we could get the reflections of these functions. It would look like this, or this, or maybe this. And that's a picture you're going to see. But these are the functions in what we would call the family and might be a little hard to read that. It's a family y equals b to the x for various b values. I don't know if any of that got recorded. Let's push a button and see. What do you think the x coordinate of this point should be? Just show me with your fingers. Okay, 6. What do you think the y coordinate should be? 8. Okay. Good. Okay. Doesn't matter what they are, as long as they're reasonable. Okay, as long as they're both positive. Actually, this could be negative, this needs to be positive. Okay. Now, there's a 0.68. So I'm going to ask you, go ahead and sketch that graph, label some 0.68, and show me where the 0.10 is. I'm sorry, 0, 1. I do that all the time. Here's the 0.01. So if 6.8 is here, well, I mean, you could divide. Here's y equals 8. You didn't have to do this, but here's y equals 8. So we cut that in half and get 4, cut that in half and get 2, cut that in half and get one, so one ought to be here. And, everybody did a pretty good job of locating where 0, 1 would be, right? So here's a point 0, 1. Now to do an exponential curve, you got to basically start on the x-axis, and then it's at some point, we aren't actually on the x-axis, but as you go to the left on an exponential curve, the values get small very quickly, so you can't tell that they're not on the x-axis, even though they are. Okay, so we kind of trace along the x-axis till we think we got to start coming up a little bit. And we do something like this, and both of you have, or everybody has curves that look much like this. Okay, so can you estimate all this curve G? Let's estimate G of two and G of 4. Okay, I didn't look at all the details, but it looks like you're doing real well. Okay, so I'm going to draw this line. I don't need it to estimate, but this would be my x equals 6 line. And everybody's got like an x equals 4 line and an x equals 2 line. And it looks like you did at least as good a job as I did at splitting this interval into 3. So it's quite good. Okay, so the x equals 2 point is here, and the x equals 4 point is here. Now, if I believe my subdivisions, and they're not totally accurate, I get a value here, so I get a y equals something here. And you're probably going to get something different than I did because your curve is going to have a slightly different shape. And you're going to get a y equals something on this dotted line, right? And that's going to be your G of 2 and your G of 4. So the y you get here is your G of 2. And the y you get here is your G of 4. So what are your estimates? Unfortunately, that wasn't recorded, but go ahead and figure this out, and I'll just repeat what I said. Okay. So here are my projection lines. My estimates are G of 2 equals 2 and G of 4 equals 4.5. Now, those aren't totally consistent, and I can see that, but those are my honest estimates. Now, G of X, I'm saying, has the form, it's an exponential function. It's got to have the form b to the x, provided it goes through the point 0, 1, because if x is 0, you're going to get b to the 0, which is 1. Okay, so b to the 0 always equals 1, so the point does, or the graph does go through the y-axis at y equals 1. Okay, the point 0, 1 is on the graph of this function. Okay, now it's also going to go through the point 6, 8. So my question is, what equation do we get if y equals 8 and x equals 6? Can you write that equation down and solve for b? Now you might have a little bit of problem solving for b, but it's actually quite simple. So if you have a problem with that, we'll resolve it, but let's see if you can do it. Okay. Network's still connected, so we're on a roll. Okay, well, this is y equals b to the x. So we just bring this over here. It doesn't take much room to do this, fortunately. So I can come right over here and I can say, okay. Y equals b to the x equals 6, and y equals 8. So we get 8 equals b to the 6th, not 6 to anything. We just replace x and y with their values. So this is b to the 6th. And now we solve. And I'll write it b to the 6th equals 8 because the thing we're solving for is usually we're kind of in the habit of putting it on the left. So anybody want to have an idea how to solve that? Oh, we're almost out of time, so I'm not going to drag it out of you. And, you know, this is something people aren't all that much used to doing. I want to leave myself a little more room to write it out clearly. B to the 6th to the 1/6 by your rules for exponents is b to the 6th times 1/6, and 6 times 1/6 is 1. Now, what's 8 to the 1/6 power? You can do that in your head, can't you? Well, no, I can't do that in my head very well either. Actually, I can. 8 to the 1/6 is approximately 1.414. Now, I just lucked out because of the numbers that the class chose. So I just happen to know what 8 to the 1/6 is, because I know what 8 to the 1/3 is and what the square root of 2 is. Okay. Y equals g of x, and that's approximately 1.41 to the x. Thus, g of 2 is 1.41 squared, which is very close to 2. And sorry I had to step up, but thank you for choosing these numbers, because I was actually able to show off and get this thing to 4 significant figures. I didn't realize that it was going to turn out to be easy, because it's pretty tough to take the 1/6 power something. Now, what we did to solve this, we got b to the 6th equals 8. We raised both sides to the 1/6 power, because if you raise a power to a power, you multiply the powers. 6 times 1/6 is 1, so b to the 6th to the 1/6 is b. Now, that's something you're going to have to ponder. But that's 8 to the 1/6, and I know that 8 is the cube of 2, so 8 to the 1/3 is 2, and the square root of 2 is this, and that's 8 to the 1/6. Now, look at what that does. It makes me look like I know what I'm doing, because what did I estimate here? I estimate g of 2 is about 2, right? Well, g of 2 is 1.41 squared, which is 2, right? And g of 3 or g of 4 yeah, I just wrote 1.41 because I didn't have a lot of room. Could have written 1.414, but it's approximate anyway. And g of 4 equals 4. Now, I estimated g of 4 equals 4.5 because I didn't want to come off. Obviously, I knew it was 4. Well, actually, if I'd have thought about it, I would have, but, because of the doubling time and stuff, but, okay, there we have it. Now, that's a full circle. We see how to find the value of B. We do a point on the graph. Okay, as long as we go through the 0.01, and if we don't go through 0.1, well, we'll look at that later. Okay. But that gives us 0.68. Just plug into this equation with the coordinates we have. We get an equation that we can easily solve if we remember this trick. We get a function. So what I'd like you to do just on your own is take your estimates. Okay. This has got to be the function because I gave you the 2 points. See how your estimates do with this function. I'll say they'll be pretty close because your curves look pretty good. And I think you're pretty good at estimating. Okay, very good.